In this paper, we present our training methods for variational autoencoders, VAEs, and generative invertible view transformations, GIVTs. We train a continuous beta VAE with a Gaussian encoder and prior, where the encoder predicts the mean and variance of a multivariate normal distribution for the latent representation. The VAE decoder then maps the latent sequence back to an image. We compute the KL term in the evidence lower bound, ELBO, in closed form, and base the reconstruction, likelihood term in the ELBO on a mixture of mean squared error, MSE, perceptual loss, and generative adversarial network, GAN, loss for image generation. For GIVT training, we flatten the latent representation into a sequence of real-valued vectors. We modify the standard transformer decoder architecture by replacing the embedding lookup tables with a linear layer for input projection. At the output, the transformer predicts the parameters of a continuous distribution, specifically a K-mixture Gaussian mixture model, GMM. Our GIVT model predicts 3 decay parameters, means, scales, and mixture probabilities, for D-scalar GMMs. We evaluate the predicted distribution using the standard cross-entropy loss. We also introduce GIVT causal, where the latent representation is flattened into a sequence line by line. The GIVT predicts each d-dimensional vector conditioned on all previous vectors. We ensure causality by masking self-attention layers. For class-conditional image generation, we prepend a CLS vector to the input sequence for each class. In GIVT mask GIT, we randomly mask the input during training. The masked tokens are replaced with zeros in the latent representation, and the masked representation is embedded with a single dense layer. We concatenate special tokens, mask, and unmask, in the feature dimension. During inference, we run GIVT either causally or as in mask GIT. We explore different sampling algorithms, including temperature sampling, nucleus sampling, and beam search. We use variance scaling to adapt the standard deviation of the predicted Gaussian distributions for temperature sampling, and employ rejection sampling for density-based classifier-free guidance, DBCFG, to sample from the unnormalized density predicted by GIVT. Our proposed GIVT method does not rely on quantization and achieves image generation without discrete codes. We demonstrate the effectiveness of our method through a series of experiments.